Here we have a boat, and the boat is, if you can look at my little coordinate system here, this boat I've placed at the origin, and it's just to show directions, north, south, east, and west. And the boat has an engine that will propel it to the north at 6 meters per second. But the current in the water is pushing the boat to the east at 2 meters per second. So if we want to determine what is the velocity of this boat, it can't go in two directions simultaneously and be remain intact. So how we resolve this is we add these two velocity vectors. And the addition of vectors can be done graphically or algebraically. Now, I find the algebraic version is what you're going to be primarily concerned with, and I will show you how the graphical method works, but personally I use the graphical method for a quick check or an estimation, but when I want a quantitative solution, I use the algebraic method, much quicker. So to do this graphically, the first one is to note that, and you probably have been able to determine this already, we represent vectors with arrows, and the length of it it represents the magnitude. And obviously it points in its direction, so it points to represent its direction. The length represents the magnitude of that vector. So if I wanted to add these two velocity vectors on this boat, and I did it graphically, then what I would do is I would set up a scale to represent 6 meters per second. For instance, 1 centimeter is equivalent to 1 meter per second. So this vector would be represented as 6 centimeters in length. Let me differentiate these. Let's call this red vector, vector 1, and this blue vector here, vector 2. I would represent vector 1 with 2 centimeters. So that would be necessary for this. And then the way that we add these vectors is graphically is with what head to tail method. Or there is a parallelogram method, which hopefully will become obvious as we work through these. So let's take the first vector, vector 1, and in fact it doesn't matter which vector you begin with. In fact, let's begin with vector 2. It doesn't matter which one you begin with, but most of you are familiar with copy and paste. So if you could imagine that we copied vector 2, we're going to paste vector 2 on our origin, at the tail on the origin, and orient it exactly as it is in our original scenario. So there's vector 2. And to add to vector 2, we're going to copy and paste vector 1 exactly in its orientation, which is due east, only instead of pasting its tail to the origin, we're going to paste its tail to the head of vector 2. So to the east, 2 centimeters. In this case, vector 1. Now, once we have done that, the sum when we add vectors is known as the resultant. L. And the resultant is represented on our graph from the origin to the head of the second vector that we placed. Now I see that I began with vector 2 and placed vector 1 second, but this is our resultant. Now, to show you that it wouldn't matter which vector you began with, all right, if I started with vector 1, I would copy and paste it in its original orientation, and then vector 2 would have been copied and pasted to the head of vector 1 in its original orientation, and then the resultant is found from the origin to the head of the second vector. So that's our resultant. Now, to do it graphically, you would want to measure the lengths, and if the lengths were properly scaled, then you could measure the length of this resultant vector here, and that would give you the magnitude of the resultant velocity. And then you could measure an angle to find direction from either of your primary axes. So if we look at this example in the center, where I started with vector 2, now that I have the resultant and I know that vector 2's magnitude was 6 meters per second and vector 1's magnitude was 2 meters per second, these are just two sides of a right triangle. So here's my two sides. The hypotenuse is the resultant, and if we want the direction of this resultant vector, let's find, I don't know, this angle. So we know the angle that we are looking for, the opposite side, is 2. The adjacent side is 6. Pythagorean's theorem will give us this resultant and therefore this velocity of about 6.3 meters per second. And since it is a vector and it's not on a primary axis, then simple positive or negative doesn't give us its direction. We need to stay in degrees where that vector is from a primary axis. So finding this angle, that is opposite and adjacent, that's a tangent function, but I don't want the tangent of that angle, I want the angle in degrees. So that is an inverse tangent function of opposite, which is 2, over adjacent, which is 6. And if we toss that in our calculators and we are in degrees mode, about 18.4 degrees. So our velocity is 6.3 meters per second at 18.4 degrees. Now let's look at the angle that we measured. We measured this angle from the north direction. So from the north, our angle is in the eastward direction from the northern axis. So we would write this as 6.3 meters per second at 18.4 degrees east of north. This is the sum of those two added vectors. Now, graphically, if we measured the lengths, we could use a protractor to measure either of these angles. If we had instead decided to go with this angle, we could have said that that was, instead of 18.4 degrees, that would have been, 71.6 degrees? We could have said 71.6 degrees north of east, that is the same direction as long as we state what is the angle and from which primary axis in which direction. Now later on we'll discuss other ways to express these angles, but for now let's state them in these terms. So that one was relatively straightforward. Both of those vectors lie on a primary axis, and we didn't need to worry about vectors that were not on a primary axis. Now that's easy. We made our own coordinate system. I intentionally made this simple. So to do it graphically, we simply copy and paste. Now that parallelogram method, I think most of you can see that I could take, if the vectors that you are adding have their tails, now guys, this, to make sure we're straight here, this pointy end is the head, okay, and the back of it here is the tail. If they have their tails on the origin, then I can simply do this and make this parallelogram, in this case it's rectangle, and my origin is from my resultant is from corner to corner, and then measure the angle for the direction. But graphically, yeah, we could get out graph paper and use rulers and protractors and do all this by hand, but I think you see that a quick estimation of where the solution lies is really where the usefulness comes in for these graphical additions. So we just added two vectors. We had two velocity vectors, and we added those vectors to find the resultant, right? Which in this case, they were velocity vectors, so we found the actual velocity of the boat here. Now, let's take a look at an example where the vectors are not on a primary axis. So here I've taken the same situation, I just didn't draw the little boat in here this time. And imagine a boat at the origin, and this time the engines are propelling it in a direction that is 6 meters per second north of east. And let's call that one vector 1. And the current is pushing it 2 meters per second in a direction that is 25 degrees to the north of west. So we'll call this one vector 2 over here on the left, vector 1 on the right. And we have their magnitude and direction. So if I wanted to add those two graphically, I could copy and paste. So let's start with the vector 1 exactly as it is oriented. Let's copy it and paste it onto this little coordinate system on the right side here. So we have this vector 1. Now I'm not using a ruler, that's going to slow me down. So just imagine this is vector 1, and it is 30 degrees above the, to the north of our easterly direction. So there's vector 1. Now I'll go back, the head to tail method, I'll take vector 2 and imagine copying it, and it's 25 degrees above the west. Well, this horizontal line represents the westerly direction. So 25 degrees above that, from the head of vector 1, vector 2, where that angle is 25 degrees. Now, both vectors are laid down, head to tail, so our resultant is from the origin to the head of the second vector. That's the resultant. We could measure an angle. We could measure this angle and say it's that many degrees to the east of north. We could measure this angle and say that it's that many degrees to the north of east. Either one will be fine. We could measure its length for the magnitude. But that's good for estimating an answer. I would look at this initial diagram over here, and I would simply imagine in my mind copying and pasting vector 2 to the head of vector 1, and in my mind sketching in the resultant, and I would know, well, this resultant is in the first quadrant, and move on with my life and do it algebraically. So to do this algebraically, what we need to do is we need to find the components of each vector. So to show you what I mean, vector number 1 is 6 meters per second at 30 degrees above the east. So it has an x or adjacent component that is easterly. Let's call that vector 1's x component. And it has a y component that is northerly. Let's call that vector 1's y component, y1. So when I say components, I really, it is as simple as thinking two sides of a right triangle. This is the x component, and this is the y component. So the components of the vector, well, the vector itself is the hypotenuse. It was the original vector in our drawing, the 6 meters per second, 30 degrees above the axis. That's the hypotenuse. The components are the adjacent and opposite sides of the triangle that hypotenuse makes with one of my primary axes, in this case my easterly direction. So vector 2, and this one's a little bit smaller, I see. I'm going to zoom in on it just a little to try to sketch this in here. Vector 2 has an x component starting from the origin that points in the negative direction, but that is x for vector 2, and a y component that is from from the x component in the positive direction. That's y for vector 2. So two sides of a right triangle, we know that the hypotenuse is 2 meters per second. So each vector has an x and a y component. So all we need to do is to figure out what these components are and add them. So once we add them, we will have the components of the resultant. So what we're doing, just to be clear, is we are going to add these algebraically. Right, to add vectors algebraically. I don't know if that's spelled correctly or not, but there it is. To add these algebraically, the first thing we want to do are find the x and y, and in this case I know the north, south, and east, west components of the vectors. Then we want to sum the x components this sum is the x component of the resultant. And then we need to do the same thing, ditto, ditto, for the y components. So it looks to me like y1 is a hypotenuse of 6 and an angle of 30. This is an opposite side. For y1, it is opposite my angle of 30. So with the hypotenuse, that's a sine function. So sine, that sine function is 6 sine 30, and the sine of 30 is a half. So y1 has a value of 3 meters per second, and it is in the positive direction. Look at the way that the component arrow points. Okay, x1, the x component is a cosine function. It's adjacent, so 6 cosine of 30 is about 5.2. Over here for vector number 2 on the left side, its x component, and I know I've drawn myself small here, so this x component here, x2, there's a hypotenuse of 2 and the angle is 25. So the cosine function, 2 cosine of 25, has a magnitude of about 1.8. But before I write that magnitude down, this component arrow points to the west. Now, I have to differentiate east and west mathematically. So if you can imagine, instead of an east, west, north, south coordinate system, imagine an XY coordinate system. One direction would be positive, say to the east is positive, and to the west is negative. So I'm going to do the same thing here. I have to be able to tell the difference algebraically between east and west. So I'm going to call east positive and west negative. And vector component x2 points in the negative direction. So it's incumbent upon you to know that one's negative. So when you put that function in your calculator, 2 cosine 25, and you get a magnitude of 1.8, that's going to be in the negative direction of 1.8 meters per second. And then the y component over here, y2, is a sine function, so 2 sine 25, that's let's call that 0.85. So I have determined the x and y components. So I'm going to have x1 and y1, and I'm going to have x for vector 2 and y for vector 2, and I'm going to add these up. So for vector 1, its y component was 3 meters per second, and that's a positive value. It points upward, so that's 3 meters per second. Y for vector 2 is this, that's y, is this 0.85, and it also pointed upwards in the northern or positive direction, so north positive, south negative, just like I did east west. So 0.85, and it looks like if I add these two, I will find y total, y sub t, y total of about 3.85 meters per second. And for the x's, to sum those, looks like the x component for 1 is 5.2, and the x component for 2, which we know is negative 1.8. So when I sum those, that's about 3.4. So now I have the x, what I've called here, I've designated x total and y total. I have the x and y components of the resultant that I'm looking for. So if those are the components, right, these are the x and y components of the resultant. So let's find what that resultant is. So here's my north, south, east, west, or positive, right? East is my positive direction, west is my negative direction. All right, positive north, negative south. Here's the origin. Looks like we have a y component, and again, it doesn't matter if you begin with the x or the y. It doesn't matter. At this point, we're doing what we did in the very first example. Let's start with the y. We're going to go in the y direction for the y-axis in the positive direction, 3.85. So there's 3.85. And then we're going to go in the x positive direction, 3.4. And here is my resultant. Now, this one is simple enough. This resultant, which will be the velocity that we are adding here, looks like Pythagorean's theorem will give us that. 3.4 squared plus 3.85 squared. And so that's about, let's call it 5.14 meters per second. And we need a direction. This is a vector. We can't say positive or negative. We can't say east or west because this resultant is not on a primary axis, so positive or negative won't work. We need to express an angle. So if I use the opposite and the adjacent side, now guys, I know all three sides at this point. I could use any function that I wanted, but this opposite and adjacent, I want the angle, so the inverse tangent of opposite over adjacent gives me an angle of 41.4 degrees or so. So this velocity, 5.14 meters per second at 41.4 degrees, and that angle was from the north in the easterly direction. So east of north, this is the resultant.